Good morning, intrepid calculus explorers. We're back again. This is our second to last lesson for really the entire year, it seems like. Or second to last new lesson, I should say. We still have plenty of review to get through. The theme of this unit has been 3D integration applications, or how can you find the volume of three-dimensional shapes that we create from two-dimensional shapes. Previously, we took a flat base and we built shapes up off the screen. Today, we're going to take shapes and we're going to build them really around and through the screen, and that's a little weird to think about, so we're going to get to picture drawing first. So your goal is for both problem 1 and problem 2 to do this without me, so you should pause this for about 2 minutes or so once you get the directions, and then see how you did. So your goal is to draw the solid of revolution that's created when you rotate this following green area around the x-axis. Now when I say around the x-axis, I don't just mean from here to here. I mean we're going to take this area and we're going to rotate it all the way around 360 degrees. So go ahead and pause this. Try to draw both 1 and 2, answer the questions to the right, and then unpause and we'll come back together. Alright, hopefully you did something like this. What you end up doing here is, and the way I like to draw these, is I take this boundary line up here and I like to reflect that boundary line first, so something like that. Then I'm going to take this area, and in order to show this area is rotating around, I'm going to go ahead and draw some circles. And I'm just going to draw a circle here and then show that it flips underneath like that. And here is my circle again. And let's just do one more kind of at the apex over here. And then this one I'm going to keep solid because maybe that's the bottom right here, right? And I'll shade it in just to give it some dimensionality. So yeah, there's our shape. That's looking okay. Now the next thing said draw a cross section when you cut it vertically. So you imagine you're taking that saw and you're just slicing it through and just peeling open this shape over here. And the question is, what three-dimensional shape or what shape are you going to get when you cut it vertically? Well, you can already see, I think, if you were to slice this vertically, that we would end up with a shape that looks like this, right? And this is, of course, a circle. Mine is a little distended, but either way, there's your circle that would pop out. And this, I don't know, what would you call this? Like a pyramid, maybe? Something like that? So, the next thing that we're going to do is problem 2. Problem 2 is going to be something super similar, and I'm going to do the exact same thing. I'm going to take the shape and I'm going to reflect it over the x-axis. So this one could be a little bit trickier to draw, but I'm going to go ahead and let's see, it's right about here, kind of goes down and then goes something like that. That looks pretty decent, I think. Okay, so let's see, it kind of ends here, ends over here. Oh, I should have done better with that. Oh well. Okay, and then we need to give it some three-dimensionalness. I'm sure that's a word. So I'm going to go ahead and do this, something like that. Then we're going to go this way, and then this is going to be my solid base. There we go. Okay, so looking at that then, I don't even know how you describe that shape. Some people have said it's like it's a really cool coffee table. Others have said it's like that, I don't know, like African drum. I don't know. Either way, it's a cool looking shape. But the important part is when you cut this vertically again, you also end up with a circle. Okay, or if we put it in better perspective, it's actually a circle. So, what's interesting then is anytime we create a solid of revolution, meaning a solid where we revolve an area around the x or the y axis, the cross sections will always be circles. Always, always. So in the past, we've built any cross section we wanted straight up the page, but somewhat unshockingly, when you spin an area 360 degrees, it will create multiple stacked circles on each other, right? I only drew 4 circles here, but hopefully we can see that this is made up of, oh, I don't know, maybe an infinite number of circles being added up, and maybe that will give you an indication of how integration is involved. So I'm just going to do one example here, and then after this one example, we're going to pause the video, or actually stop the video, and I'll create part 2, but then you'll get some practice problem. So, how do we actually find the total volume of one of these cool revolutions? Well, we build up essentially from cross sections again, right? We're going to find the area, two-dimensional first, of one circle. We do have to remember every circle is a different size, but we're going to find the area of one circle in terms of x, or y if you're going around the y-axis. And then we're going to give the circle some infinitely small depth, just like cross sections, and we're going to call that depth dx. And then we're of course going to multiply our area, two-dimensional, times dx, three-dimensional, to get volume. And lastly, we're going to sum up the volume of every disk using an integral. So the steps are really similar. However, the setup is going to be a little different. I picked a problem that's a little more complicated. I wanted to give you a more complicated example and then have you guys try some easier ones. So let's see what we can do. Region R is bounded by all this stuff. Find the volume of the solid when R is revolved around the x-axis. Well, one of the problems of this is we actually want to see what the graph looks like first. And so you're actually, for maybe the first time this year, going to have to graph a parabola somewhat accurately. Okay, so let's go ahead and try to break down this parabola first and see what information we can get out of it. So y equals x squared minus 4x plus 5. I don't think this factors either. Now, if it doesn't factor, what that probably means, well, it means a couple things. It could either mean that our graph never crosses the x-axis, there's no real solutions, or it could mean that it crosses at really gross numbers you can only find using the quadratic formula or completing the square. As far as I know, there's never a case in AP Calculus where you have to use the quadratic formula, so it's maybe my guess here that it never crosses an axis, but we can be a little bit more sure. But let's start graphing this. We know we have to go from 1 to 4 on the x-axis. So when I graph this, let's see, we're going to give it a decent amount of space here because we're going to have to flip it over, right? So I didn't like that. So we're going to go, oh, it's much better. We'll call this 1. We'll call this one all the way over here 4. We could at least find the corresponding y values for this parabola just by plugging in 1 and plugging in 4. So if I plug in 1, 1 plus 5 is 6, 6 minus 4 is 2. And if I plug in 4, 16 minus 16 is 0, that's 5. So I only need to go all the way up to 5. So here's 1, 2, 3, 4, 5, and we should do the same thing down here. 1, 2, 3, 4, 5. Okay, so we said 1, comma 2, and we also said 4, comma 5. Great, but then the question becomes, does our parabola dip down here, or does it stay above the axis? It's going to be much easier if it stays above the axis, but we're not sure yet. And what's really going to help us then is the vertex here. So to find the vertex of a parabola in standard form, I'm sure we can pretend to remember that a vertex, if we consider a vertex having h comma k as our components, that h is always going to be negative b over 2a. That's a thing we might remember. So negative 4 is positive 4. 2 times 1 is 2. So it seems to me like my vertex is going to be 2 comma something. How do we find the something? Well, we of course just plug it in. 4 minus 8 is negative 4. Negative 4 plus 5 is positive 1. All right, so our vertex occurs at 2, and I should probably equally space this out. So we have 1, 2, 3, there we go. 2, 3. So we have 2 comma 1's the vertex. Now I'm pretty convinced it does not go below the x-axis. And by symmetry, if this is 1, 2, 2, 1, this has got to be 3, 2. Here is my beautiful parabola. Now again, most problems are not this much work, but I wanted to remind you of how to graph a parabola in case hypothetically it came up later on today. So there's that. All right, now let's go ahead and actually get our region R. So region R is just going to be this space here. It looks very similar to problem 2 on the previous page. I think all we need to do at this point is take this and revolve it around the x-axis. Sometimes you'll see a little like arrow like this showing you which axis to spin it around, because sometimes you could spin it around the y. And in fact, we'll do that later on too, but there's not going to be anything new there. So let's go ahead and reflect it first. It looks like it's going to be here, 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 and then this one is at 5. 1, 2, 3, 4, 5. All right, and that's going to make this a little bit easier to draw. And then let's give it some three-dimensionality. So I'm going to do this. Easy to draw circles if you have the corresponding points, and this one's going to be solid just to show this base. You could, of course, do it the other way, but for whatever reason, I end up doing it this way every time. Okay, now, what are the steps? Well, the first thing I like to do is, of course, create the area function. In order to create the area function, I always like to start with a circle. Okay, it's always going to be a circle here. And we know, of course, that the area of a circle is pi times the radius squared. But I'm not going to be using radius in here. We're going to need an x value of some sort. So let's figure out what is that x value. Well, if you draw this shape, this three-dimensional shape fairly accurately, I can take any one of these circles and say, well, the radius, of course, could be drawn side to side. It could be drawn diagonally. It could even be drawn straight up and down. All of these are radii. And what I'm going to do here is find an easy way to make sure that the radius is the same every time. So notice that if this is my radius, it stops at the x-axis. Radius, radius, radius. All of these have a consistent radius, and that radius is the distance from the x-axis to the function, right? Function minus x-axis, top minus bottom. It's our theme for this entire unit, that top minus bottom theme. So I think if I want to find my area function for a circle, then it's just going to be pi times the radius squared, where the radius is just the top function minus 0. My top function, maybe I'll say that this is f of x to save me some time. It's going to be f of x top function minus the bottom function, which is 0. And I would heavily encourage you, for at least for today, to write it as top minus bottom, because tomorrow our bottom function might not be the x-axis. In fact, it might not even be the x-axis today. So if we clean this up, though, once we've seen that, then my area function is just pi times f of x squared. Nice. All right, well, what's next? Well, that's my area function. All right, that's like my step 1. My step 2 then is I want to take one of these circles and I want to give it three-dimensionality. So all I'm going to do is just draw this little bit of width here on this friendly circle, right? And instead of a circle, now it's a circle that has a little bit of depth. It's kind of like a pancake, or a lot of times you'll hear it called a disc. Think frisbee or a disc, something like that, yeah? So it's a pancake or a disc, and in fact this is often called the disc method, because we're going to take one of these discs and then we're going to add all of these discs up so that we make a three-dimensional shape when we stack it all on top of each other. Of course, this itty-bitty width, this infinitely small width across the x-axis, is dx. So my second step, as always, is going to be to create the volume function. My volume function is going to take the area function, that's two-dimensional, and multiply it by a third dimension. And then last but not least, and I'm going to do this way down below because I think I'll need the space here, my third step is, of course, to add up all of these disks. I don't want the volume of just one disk, I want all of them. So we're going to have to sum up pi f of x squared dx from where to where? Well, the disks start at 1 and they end at 4. 1 to 4, and we're looking okay. Now, the problem here is they said find the volume of the solid, and we have not found the volume of the solid. So we are going to find the volume by actually doing the integral, and they gave us the answer down here. So you actually might want to pause this video right now and see if you can get that answer. And then when you're ready, or if you get stuck, unpause it and you can take a look at my work. All right, hopefully you've given this a shot. So I'm going to go from 1 to 4 pi, let's see, f of x, I actually need to write this one out, x squared minus 4x plus 5 squared dx. Okay, well, from here, let's see, what do I need to do? To take the antiderivative, I think I'm going to have to multiply all that out. Oof, that's a pain. Luckily, we're only doing one of these. I'm also going to factor the pi out front. It's pretty irrelevant for this, and let's do this. This times itself. Ooh, buddy, there are going to be a lot of those. You might even want to just organize it over here. I'll do that too. We're going to do a 3 by 3, I think. X squared minus 4x plus 5, x squared minus 4x plus 5. Okay, x to the fourth minus 4x cubed, 5x squared. And then I think we could probably get the same thing over here, minus 4x cubed, 5x squared. Do the same thing, 16x squared minus 20x minus 20x, and then plus 25. All right, so as we go through, I have x to the fourth, that one's gone. We have negative 8 of those. And then we have 10 and 16 is going to be 26 of those x's, minus 40, that should have said x squared, sorry, and then plus 25, and there's no x there. Where'd that x come from? Go away. Ha! Plus 25 dx. All right, that took an extra 30 seconds. Bummer. Okay, let's finish this off. Pi 1/5 x to the 5th minus, this one's a little bit trickier, 2x to the 4th plus, this is going to be x cubed, so 26/3 x cubed minus 20x squared plus 25. Ha, now it gets an x from 1 to 4. Okay, then you might need a calculator for this part. I probably will too. We're going to have to plug a bunch of things in. Pi, and then what do we have here? 1/5 times 4 to the 5th minus 2 times 4 to the 4th plus 26/3 times 4 cubed. I know that's 64 minus 20 by 16 plus 25 by 4. Pretty confident that's 100 minus, and then 1/5 minus 2 plus 26/3 minus 20 plus 25, and then clean all that up. If you want to, it's probably good fraction practice, but really you can use your calculator. I think you should end up here though. Just double check to make sure I've done everything right. So this ends this wonderful video. The last 2 pages of this packet, of course, are 3 practice problems. Your goal is to go through and try all of them first, and then once you're done, or if you get stuck, you can watch my second video. Thanks for your hard work, and I'm excited for the next time I can see you guys.